Hi everyone, welcome to my talk. Today I'll talk about debugging. First, a bit about myself. I work for Google and I've been using Python since 2012. Here's my GitHub and Twitter account. There are 5 parts in this talk. We'll talk about what debugging is really about. We'll go over the history of debugging. And I'll talk about 2 pain points with the current debugging solutions. Next, we'll look at a novel approach to tackle these 2 pain points. Finally, we'll talk about where do we go from here. First, what debugging is really about. When we talk about debugging, we always mean there's some type of error that we're trying to solve. And in Python, there are 4 types of errors. A program can fail to compile, it can exit abnormally, it can run but gives the wrong results. And if the result is correct, it can also consume more resources than expected. Among these 4 types of errors, the third one, which is the program can run but gives wrong results, is the most common one, and often the type of error that we spend most of our time debugging. So in this talk, I'll be focusing on this type of error. And in this context, no matter which approach we take in debugging, debugging is just about figuring out why our program gives the wrong result. This may sound very trivial, but it is very important that we realize this fact before going to later sections. Next, we'll talk about the history of debugging. This is an image of EDSAC, a computer built in the late 1940s. As you can see, the computer is very huge. And there is an article talking about how programmers back then debugged with EDSAC. So I'll just read the quotes here. Programmers single-stepping through the program and observing the contents of the memory and registers on the monitor tubes. The monitor tubes are the things that's showing on the right. As you can see, observing the monitor is not really a good way for debugging. So the programmers of EDSAC developed something they call software aids, which includes post-mortem dump routine and interpretive trace routine. These are essentially the loggers we use today, but very primitive. Then in the 80s, debuggers came along. The first version of GDB was released in 1986, and other debuggers also appeared in the 80s. Today we have 3 major ways for debugging. They are print, logging, and debugger. First, we'll look at print. Guido once said, often the quickest way to debug a program is to add a few print statements. Linus said, I don't like debuggers, never have, probably never will. This shows that print has some good characteristics that they like. It is available out of the box always. There's no redundant information. You just get whatever you print. And normally, print won't change the program's behavior. And print can help answer this question. Has this line of code ever run? But print also has some drawbacks. It requires decent familiarity with code. You have to know where to put the print. It requires code modification. It lacks context. And it is hard to manage output. Next, there's logging. Here's a screenshot of how we use logging in Python. So logging is more configurable than print. You can just control where to put the logs. Also, it is easy to manage output. Logging also provides richer context. You can have file name and line number, things like that in the logs. But logging is not perfect. Configure a logger is sometimes cumbersome. And you have to write a lot of boilerplate code to properly configure a logger. And if you choose to use some third-party logger, it may not be available out of the box. And still, context is not enough in the logs. Finally, there's debugger. So debugger is, with no doubt, the most powerful way to debug, and it has the most features. It doesn't require familiarity with code. You can just step through the program from the entry point. It can help you find root cause more easily because you can like set breakpoints and look at the values of those variables. There are some drawbacks with debuggers. First, it depends on certain debugger always depends on certain libraries, IDEs, or editors. So if you change a computer, it may not be there. And debugger has some learning curve. Also, there's no way to persist information in a debugger. We'll talk about that next. There's also could be performance issue brought by the debugger. Next, let's look at the 2 pain points with current debugging solutions. So, pain point 1. There's no tool that is as easy to use as a print, yet as powerful as a debugger. What does that mean? We have looked at these 3 ways of debugging and can draw a table like this. There are 2 columns with this table. First is the effort required to use this way of debugging. The other column is the information this tool provides. So the first row shows that print requires the lowest amount of effort to use, but it also and it provides the simplest information. Login requires a bit more effort to configure and provides a bit more information. Debugger requires the highest amount of effort to use because you have to set breakpoints, you have to step through the program, you have to learn how to use it. On the other hand, it provides the richest information. So look at this last line and the question mark here. There's no tool that requires the lowest amount of effort but can provide very rich information. This type of tool doesn't exist yet. Pain point 2. Recall what we mentioned earlier. Debugging is about figuring out why our program gives the wrong result. And existing tools actually only give clues, but they don't tell you why. We'll look at what that means. Suppose we are debugging a program, c equals a plus b, and c should be 1000, but instead it's 1200. This is how we usually debug. We can set a breakpoint at this line. We run the program, and we inspect the values of a and b. So we figure out whether the error lies in A or B, and we just repeat this process until we find the root cause. We could do it in another way. We can set a breakpoint at the programmer's entry point. We then step through the program until we reach c equals a plus b. And I think since we use debuggers, we all use debuggers, and we know that there are many manual effort involved in this process. So we need to monitor relevant variables, right? And we have to memorize the results at every step. We have to compare the values of those variables with the expected values. And since there's no way to persist in the information we see from debugger, we have to use our brain to do all this. And this is a huge overhead to our brain, and as a result, made debugging less efficient and sometimes frustrating. So I think the problem is very obvious. It is because debuggers only give clues without telling why. And that's why we have to do all this manual effort. And if there's a bigger problem, is that we don't even think it is a problem. Next, we'll talk about a novel approach to tackle these 2 pain points. Like said, an ideal debugging tool should be easy to use and provide rich information. It should tell you why a variable has a wrong value with very little human intervention. So for a moment, let's just forget about the existing tools and their capabilities and think about one question. Who has the information we need for debugging? And the answer is the Python interpreter. So the question becomes, how do we pull the information out of the interpreter? As you can probably imagine, the interpreter knows all this runtime information. It knows everything that happened in execution. And this information is actually baked into the bytecode. And we'll see what that means. So bytecode, so Python is an interpreted language. What that means is it is not compiled into machine code, but interpreted along the way. And bytecode is what's get interpreted. So if you use the this module, you can see that C equals A plus B actually consists of this bytecode. And we'll explain what that means in the next slide. So to understand the bytecode, we have to learn a bit more about the virtual machine. So CPython's virtual machine is a stack machine. What that means is CPython uses a stack to do all the computations. So at the start of the program, the stack is empty. And then we encounter the first bytecode, which is load name with an argument A. And what it does is it loads the value of A into the stack. So the stack now has a value, which is the value of A. And next is load name B. It does the same with the first the load name A. So now stack has two items. Next bytecode is binary add. What it does is it pops the two items from the stack, adds them together, and puts the result back. So now there's one item on the stack, which is the sum of A and B. Finally, there's this bytecode store name C. It pops up the item on the stack and assigned to C. So that's how C equals A plus B is executed on the bytecode level. So we know what this bytecode does, and how do we use them for debugging? To do that, we use an API called setTrace. So what it does is basically you give setTrace a callback, and you can let the callback be triggered every time a bytecode is executed. So here, since there are 4 bytecodes, and the callback will be triggered 4 times. So from the callback's perspective, it see that load name A is called, load name B is called, binary add is called, and store name C is called. So now we know this information, and but we still didn't answer the question of using it, how to use it for debugging. So I'll explain how that works. So we said that callback can see this 4 bytecode, and it does something more. So for example, when it sees the bytecode of load name A, it can inspect A's value. For example, let's say its value is 1000. It does the same with B, and then it sees the binary add bytecode. So since we know what binary add does is to pop the 2 values on the stack and add them together and put the sum back, so we can record this information. It will be useful next. So next comes the store name C bytecode, and we know 2 things. First, we can inspect C's value. Let's say it's 1200. Then, since we know that the previous bytecode is binary add with 2 arguments, A and B, so we know that C's value comes from A and B. because A and B is the item that's still on the stack. So, and with this information, we can draw a graph like this. We can put A and B on the top, and they have these arrows linked to C. And we have their values, so we can also put the values there. Suppose we know that the 200 is the correct value for B, and we can see that it is actually A's value that caused C to have the wrong value. So this example may not seem very interesting, but imagine we can do something like this. So what if we can draw this graph from the start of the program to the variable that has the wrong value? And if we can draw this graph, it is very easy to see everything that happened along the way. And with that, we can easily spot what value is wrong. Like this, we can see this path of the wrong value being passed to the final wrong value, which is C. So I built a tool around this idea called Cyerbrain. It just does what I just mentioned. I'll do a quick demo of Cyerbrain. Cyerbrain consists of a Python library and a VS Code extension. Here I've already installed Cyerbrain, and I can do from Cyerbrain import trace. Trace is a decorator I can put on this function here. And I also installed the extension in VS Code, so I can just run it. Okay. So it runs, and it generates a graph like this. This is just exactly the graph we saw in the slide. It describes the data flow in the function. And we can see that the function has this argument word is on the top of this graph, and word gradually becomes other values. And finally, it will return a tuple here. And as we hover our mouse on these nodes, it also shows the values of each node. So it's very easy to spot what's the values of everything that happened along the way. And also, it only shows the relevant variables, so you won't get too much stuff that will be useless for your debugging. So on the right side, we can see that it prints out the real values of those nodes. Because sometimes if a value is too large, like here, there's a list that has 1,000 items. It may not fit into this small graph, but with these, this is actually the Chrome debug console. You can see the values of each item, so it is very convenient. And so Cyerbrain implements the idea of backtracing the values and identify the root cause of the bug. So Cyerbrain is an attempt to solve the 2 pain points. It is easy to use, but provides rich information. It tells you why a variable has a wrong value with little human intervention, because you can just see what happened along the way and identify the bug. I have to note that Cyerbrain is still very primitive. Right now, it only prints. It can only work for a single function, but I do have plans to make it work to trace the entire program, and by that time, it will become more useful. So finally, let's talk about where do we go from here. Now is actually a very interesting time. If you think about it, the existing tools are becoming calcified. So on the left, we see a screenshot of GDB. On the right, we see a screenshot of a modern debugger. So you may think that the modern debugger is a lot more advanced than GDB, but actually, they're not that different. The features we have with modern debuggers, like setting breakpoints, step into the program, inspect values. They all exist in GDB. And actually, the concept of a debugger hasn't been changed for a long time. There's something called DAP, Debug Adapter Protocol. It basically is a specification that defines the capabilities of a debugger. So it is very useful for tool builders. If your debugger is conforms to DAP and you build it for one editor, it can just work for the others. And that can save programmers a lot of time. But on the other hand, it also means that tools conform to DAP will never be able to provide capabilities beyond what the protocol specifies. On the other hand, we see new tools coming out. There's PySnooper, Ice Cream, Hunter, PyTrace. They provide an automatic way to do print so that you don't have to add print manually. We'll see an example of PySnooper in the next slide. There's also Birdseye, Thonny, and Python Tutor. They provide a graphical way of debugging, and it can help you visualize expressions or data structures. Also, there's Cyerbrain. These tools are very different from what we have today. So this is an example of PySnooper. You call with PySnooper.snoop. You give it a bunch of things here, and you don't need to add any print statement. It just automatically does print. So you run it, and it prints out the changes of local variables. As you can see, there's lower is changed, up and upper, and also mid. So this is more convenient than manually adding those print. So why do we need to care about this? I think these new tools share the same goal of reducing programmers' work in debugging. But beyond that, they're both trying to pitch the idea to people that the current standard way of debugging is not good enough, that more things can be achieved with less manual effort. I think the ideas behind are even more important than the tools themselves. Dijkstra once said, the tools we use have a profound and devious influence on our thinking habits, and therefore on our thinking abilities. Imagine a world where all these efforts don't exist. Will the word debugger gradually change from something that can help you debug to something that conforms to the debug adapter protocol? This is not impossible, and we need to prevent it from becoming the truth, because we need to preserve a possible future where programmers are debugging in an effortless and more efficient way. So what can we do? We can think of new ways to make debugging better. We can create new tools or contribute to them. We can spread this talk and the ideas behind. And also, I believe in the future, there may appear some new programming languages that put debuggability as the core feature. Finally, the easiest yet hardest thing is to keep an open mind. Thank you.